This video looks at heating curves. By the end of this video, you should understand the difference between the vertical and horizontal portions of a heating curve. You should be able to calculate energy transfers for temperature changes, and you should be able to calculate energy transfers for phase changes. There are three processes that most often account for energy changes of a system: heating or cooling the system, meaning changing the temperature; phase changes like melting or freezing or vaporizing or condensing; and chemical reactions. In this video, we'll look at the first two. Chemical reactions will be looked at later. Here we see a heating curve. A heating curve is a plot of temperature versus time where energy is added at a constant rate. Since energy is added at a constant rate, we can think of the x-axis as just amount of energy added. Notice we're not really quantifying this, we're just assuming that it's being added at a constant rate. Looking more closely at our heating curve, we can label the different parts. Notice that we start at a very low temperature. Therefore, here our substance is a solid. As we increase the temperature of the solid, we're heating the solid. Notice, however, we hit a vertical portion here. We're still adding energy because we're moving along our x-axis. However, the temperature is not changing. These flat parts of the graph represent phase changes. In this case, melting, turning from solid to liquid. Once we've liquefied our sample, we can begin to heat that liquid. And then again, we see another phase change, another flat part of the graph. This one is vaporizing. Once we've vaporized all of the substance, we can then heat the resulting gas. Of course, we can also consider the heating curve in reverse as a cooling curve. Starting in this case with our heated gas, we would first cool the gas, then convert that gas to a liquid through condensation, then cool our resulting liquid, then freeze that liquid to a solid, and finally cool the solid. Now let's look at how to quantify the changes that are going on at each part of the graph. We'll start with the vertical areas of the graph, which correspond to temperature changes. Here, the energy that's added to the system goes to speeding up the particles, or increasing their kinetic energy. Since there's a change in speed, there's a resulting change in kinetic energy, and that kinetic energy results in a change in temperature, since the average kinetic energy of the sample will change. In order to quantify the energy associated with these temperature changes, we define a constant known as the specific heat constant. Specific heat capacity is the energy required to raise the temperature of 1 gram of a substance by 1 degree. Notice it doesn't matter if you're working in Kelvin or Celsius here, since the size of 1 degree Kelvin is the same as 1 degree Celsius. Here's some specific heat capacities for the different phases of water. Every substance will have its own unique specific heat capacity. It's also possible to define the molar heat capacity. This is the energy required to raise the temperature of 1 mole of a substance by 1 degree. We'll usually work in grams in this class, but always be sure and check your units. Looking at the table on the right, you'll notice that different substances have vastly different specific heat capacities. Notice that water's specific heat capacity is actually abnormally high as compared to the rest. This has a lot of biological implications that you may have talked about in your biology class. Also note that substances that we use in cooking have very low specific heat, like copper and iron. This makes sense since we want our pots and pans to heat up quickly. A low specific heat means it doesn't take much energy to raise the temperature of 1 gram of that substance by 1 degree. For instance, it only takes 0.39 joules of energy to raise the temperature of 1 gram of copper by 1 degree. This is much different than, say, raising the temperature of ice, which takes 2.05 joules to raise the temperature of 1 gram by 1 degree. Given the definition of specific heat, we can derive the equation shown here. Since we know that specific heat is the amount of energy it takes to raise the temperature of 1 gram by 1 degree Celsius, multiplying the specific heat, which is represented by C, by the mass of the substance and the temperature change of the substance, we arrive at the amount of thermal energy involved in the process. Here's an example problem to try on your own. Pause the video here. When you come back, I'll reveal the answer. Welcome back. Here's what you should have gotten. Notice we were working with liquid water here since we were in the 75 to 40 degrees Celsius range, so you want to be sure to use the specific heat for liquid water, 4.18. Now we're going to turn to the flat parts of the heating curve graph, which correspond to phase changes. Before we talk about phase changes, let's quickly review the properties of the different phases of matter. Recall that solids are high-density substances where the particles are very strongly attracted to one another. The particles move quite slowly and generally only vibrate. As we move to a liquid, the particles are able to move more, therefore they can move around each other a bit. However, they're still attracted to each other quite well. Gases, on the other hand, are characterized by very rapid particle movement. The particles are so far away from each other that they have very weak attractions between particles. So then, let's look at these horizontal portions of the graph. Notice at these portions of the graph where we're undergoing phase changes, there is no temperature change. However, we are still adding energy since we're progressing along the x-axis. So then where is the energy going? In this case, all of the energy added to the system is used to overcome the attractions between particles and move the particles farther away from each other. This results in a change in potential energy. Recall that we associated potential energy with a change in position. Since there's no kinetic energy change, there's no temperature change. The particles remain at the same speed, they just move further away from each other. Recall also in a previous video that we discussed the fact that particles that are strongly attracted to each other are lower in energy when they're closer together. Therefore, energy is required to move them farther apart. So when we put energy into a system to move the particles apart, we have an endothermic process. On the other hand, when particles that are separated from each other come closer together, the system will release energy as an exothermic process. We can quantify these changes as well. Let's look first at heat of fusion. Heat of fusion describes the amount of energy required to melt 1 gram of a substance at its melting point. It's also the amount of energy released when 1 gram of a substance freezes at its melting point. Notice energy is absorbed when we're moving particles farther away to melt the substance, but energy is released when particles are moving closer together to freeze the substance. The heat of fusion of water is 334 joules per gram. Again, every substance has its own heat of fusion, and you'll always be given these values. Heat of vaporization, on the other hand, is the amount of energy required to vaporize 1 gram of a substance at its boiling point. It's also the amount of energy released when 1 gram of a substance condenses at its boiling point. The value here for water is 2,260 joules per gram. Note that the heat of vaporization is much larger than the heat of fusion. It takes a lot more energy to separate the particles of a liquid into a gas than it does to separate the particles of a solid into a liquid. Here's an example to try on your own. Notice this example incorporates both phase changes and temperature changes, so you'll need to use both specific heat and either heat of fusion or heat of vaporization. Pause the video here and give it a try. When you come back, I'll reveal the answer. Welcome back. Here's what you should have gotten. Notice first we need to calculate the energy needed to heat the solid to 0 degrees Celsius, its melting point. This is 309 joules. Then we need to calculate the amount of energy required to melt the substance, 5,010 joules. Then we need to calculate the amount of energy it takes to heat this melted liquid to 75 degrees Celsius, 4,703 joules. Finally, we want the total energy for this process, so we add those three values together to get 10,022 joules for the entire process. That brings us to the end of this video. Let's review our goals. First, we looked at the difference between vertical and horizontal portions of a heating curve. Then we calculated energy transfers for temperature changes. And then we calculated energy transfers for phase changes.